Hello everyone, welcome to week 4's video. This week we're going to be taking the framework we've put together and we're going to actually run a model through it to see something pop up on the screen. So before we can do that, of course, we're going to need a source model. I've uploaded one to Blackboard. So if you haven't already, you'll need to head over there and download the monkey.obj. Once you've done that, we're going to head over to the project directory for our framework. And we're going to add a new folder called Assets. Inside of Assets, I'm going to create two new subfolders, Models and Shaders. Of course, in Models, I'm going to paste my newly downloaded monkey.obj. We'll fill in the shaders a little bit later. That's all we need to do for now. So let's head over to the code. And before we can really dig into the loading and rendering code, we just need to move around a couple things first. At the top of main.cpp, we have these defines, these macros for screen height, screen width, and frames per second. We're going to need to eventually set up our camera, which means we're going to need to set up our projection matrix. In order to do that, we're going to need to know our aspect ratio, and that's a division of width and height of the screen. So we can't have these here. We need to move them over to the game class so the game actually has access to them, or else we wouldn't be able to do that division where we need it. So we're going to cut these from here. Main.cpp is still going to have access to them anyways because it includes game.h, but we're going to move them into game.h right at the top here. Additionally, I'm going to delete these first two, screen width and screen height. Those aren't used and we don't need those. We're just going to stick with these ones. And I'm going to change the window height macro to 600 instead so that we have a little bit more of a standard window size. While we're up here, we might as well go ahead and include a couple things we're going to end up needing. We're going to need our shader program.h in here, and we're going to need our mesh class as well. But before we get right into it, one more thing we have to do in main. If we scroll down to the actual main function itself, around this area in between here, you probably have a glue init call, which is correct. Unfortunately, a small error in the way I saved my project means that I have a slightly different project than you do right now. So you should have glue init in here, but I'm just going to have to write that again with one extra step that I want to make sure all of you have. So whatever you have, just make sure it looks like mine. We're going to want to make sure we set glue experimental to true before the call to glue init, and then we're going to check the return value of glue init versus glue underscore okay. So if it's not okay, then of course we have some problems. So we're not going to be able to use modern OpenGL for whatever reason. So we're going to need to output an error here to notify the developer glue could not be initialized. A system pause makes sure that they have time to read it, and then we can return 0. We're in the main function, so essentially that just ends the program. So regardless of what you have or what you had, just make sure it looks like this now. One more thing we're going to add up here after glut init is we're going to add a function that requests glut to create a very specific OpenGL version for us. OpenGL itself is actually set up when the window is set up, and it's required for OpenGL to be linked to the window itself. So OpenGL actually exists only once the window pops up. I've seen sometimes somebody will be trying to call a GL function before the window exists, or they try to load something in immediately before SFML even has a chance to create the window, and all of those functions will break. So be careful not to do that. If you have in your main .cpp a static variable, for instance, if we had our game set up like this, this actually means that the constructor for the game will be called before the main function actually starts. So if your constructor for the game includes loading functions for OpenGL, those will actually all fail and you'll get really weird errors and it'll be hard to track down why those are occurring. So just watch out for that and make sure you don't do that. I'm missing this function here. We're going to have to go to the top. Pardon me, I forgot. We need to include free glut explicitly in this file. So I'm going to access my GL folder, free glut, and that'll give us access to this function call. So moving back down, glut init context version. So we have two variables here, major version and minor version, meaning major as in OpenGL 3 and minor as in point something. So I want 4.2. We can access higher versions of OpenGL right now, but it seems like from the tutorial that we had last week, everybody's end site seems to prefer 4.2, so we're just going to stick with that for now, but you can feel free to change that if you'd like. If you don't specify this, then glut will usually try and automatically select the highest version available, or in some cases it might select a lower version. So we want to explicitly have control over that. And after those changes, we're done with the main file, so we can move back to focusing on game.h. To get ready for our rendering, we're going to want to make sure that we add the data members that we need, right? And I actually just spotted a little bug here. I have to be more careful. I need to include these before GL is included. My mistake there. So let's bring those up. The reason is shader program and mesh both internally include glue.h, and glue.h does not like to be included before gl.h or glu.h, and that'll actually generate an error if you try to compile. So just make sure those are actually above this set of includes here, and everything will work out. So let's go down to the game function. If we're going to want to render, most obviously we're going to need a mesh. Let's call that our monkey. We're going to need a shader program. So we're going to need a complete representation of a shader pipeline so that we can tell OpenGL how to behave and how to render this object. It's required now that we're in modern OpenGL. So I'm going to call it pass-through because the shaders we're going to be writing today are going to be so basic that eventually they're just passing through the data with the minimal amount of transformations required to get it onto the screen correctly. Next, I'm going to need some matrices. I'm going to want one to represent the location of my camera. So I'm going to call that camera transform. I'm going to want a 4x4 matrix that can completely represent the projection or the lens of my camera. So I'm going to make a dedicated camera projection matrix. And then I'm going to make a monkey transform, which is going to essentially be the pose of the monkey itself, its position and orientation in space. And that's actually all we need. So those default constructors will take care of themselves. We can go into game.cpp, and in the initialization of the game, we can take care of actually telling them explicitly what to load. First, however, we're going to want to enable a particular OpenGL state. We're going to want to enable GL depth test. It's kind of perhaps unintuitive that this isn't enabled by default, but in fact, the behavior of objects always drawing in front of objects they're in front of is not default. The default behavior is that the object that was drawn most recently will be drawn on top of everything else. So if you want to have a proper 3D scene, of course you'll want to enable this setting. And we only have to do it once. We don't have to do it in the draw function. There's no reason to do it over and over again. But after that's done, we can go ahead and we can set up the rest of our loading. So first I'm going to load our pass-through shader. So I'm going to call load on it, and the two files we're going to be loading, of course, don't exist just yet, but immediately after this function we're going to go write them. So I'm going to be looking in a folder relative to this directory. This first parameter being the vertex shader, by the way. So where can we find it? We can find it in the directory next to the project under assets, shaders, and we're going to call it pass-through.vert. A lot of people and a lot of examples I've seen like using .glsl and have something like vs at the end of the actual shader name as a suffix, but I don't really like that format. It seems to be much easier to spot at a glance if it's a vertex or a fragment if the extension itself is vert or frag. So I've always preferred that method, but they're all just text files, so it really doesn't matter. The extension could be whatever you'd like. For the fragment shader, we're going to look into the same folder, asset shaders, and we're going to get pass-through.frag. Now, of course, this will return false if it didn't work out, and if that is the case, then we're going to output an error. So we're going to use our standard output. Shaders fail to initialize, unfortunately. In order to give the user time to read this error, as well as the full output log that this load function is going to display, we'll want to have another system pause, and then we will abort the program. Our next task will be to load the monkey itself, so we can load from file, have a similar process in here, just specify the adjacent folder of assets models monkey.obj. The file extensions are absolutely required. So a little simpler there, but same idea. And of course, if it returns false and didn't work out, we're going to notify the user. Failed to load. Insert a new line. Give them a chance to read it with system pause. And exit 0. Last thing we have to do is set up our cameras. So our camera transform is going to start as identity, of course. It was just initialized by the constructor. But we want to translate it a little bit so that we're looking towards the center of the scene where we will keep our monkey head. We'll just keep the monkey head at the origin. So we're going to want to translate by about 5 on the Z, which will move us back. Next, we can set up our projection. So I'm going to call the frustum projection function. Of course, this is all assuming that you're using Minimath, and these functions might be subject to change depending on what library you're using. But in this one, the frustum projection function requires first the field of view. I'm going to specify 60, which is essentially going to be the 90 degrees that you're used to in a video game for those hardcore FPS shooter guys out there. But this function actually requires the field of view in the vertical direction. So it's not going to be as wide. And some libraries you'll find actually need the horizontal angle, while some ask you for the vertical angle. And it can be kind of annoying sometimes because they don't necessarily specify which one they're asking for. But as you can see in the parameter, it's asking for field of view Y, so you want to make sure you don't put it too high. If you're used to the horizontal, it'll kind of inflate larger than you'd expect. So let's calculate our aspect ratio. So we're going to take the window width and we're going to divide by the window height. And notice how I am using a cast here in order to ensure that both of these are interpreted as floats. If you don't, then they're going to be interpreted as integers, and the division will not be as accurate as it needs to be. It'll be rounded, and you'll get a really funky scene, which of course won't look quite right. So our near plane we're going to set to just 1 unit. We're going to set our far plane to about 10,000, and that'll suffice for the projection. Now, this is actually all it takes in order to load these objects. It's pretty quick and easy, and all of this is completely rigid and won't explode if something goes wrong. Most of the errors are handled, and especially in the case of the shader class, it'll actually tell you if there's a problem. So before we move on and actually get started on the render function itself, let's actually write these two shaders. So let's head into our assets folder, shaders. Let's create 2 new files. I'm going to create them as text documents. I'm going to create a pass-through.vert. Yes, I want to change the file extension. And I'm going to create a pass-through.frag. I'm not going to edit these in Notepad. We installed the plugin on the first week that allow us to work very nicely in Visual Studio itself. So I'm going to bring these in. I'm just going to drag them over on top of Visual Studio, and it'll open them up as 2 of their own tabs. If you want to get these line numbers, by the way, as you do with regular files, you'll need to add that in. So if you don't have those already, you can go into Tools, Options, you can scroll down to Text Editor, and then if you find plain text at the bottom, you can toggle the line numbers box and they'll begin to show up. So the very first thing we want to do in both of these files is define the version number we're going to be using. Now that we're in modern OpenGL, the version numbers correspond exactly with the major and minor versions of the core OpenGL profile you're using, with 0 at the end. So we're going to be using 420 and 420 for each of these. You want to make sure that you don't mix and match. Weird things can start happening if you're using a 330 shader, for instance. It's not recommended. So inside of our vertex shader, we know that our task is to transform the vertice through a few various spaces. We've seen that a couple weeks ago with the mathematical pipeline of OpenGL. So this is what OpenGL was always doing for you behind the scenes when you were using immediate mode, and it was using the model view matrices and the projection matrix from the stacks to do this work. But now we're going to be using uniform variables in order to push our custom matrices through to the vertex shader, and we're going to multiply them ourselves. So we're going to have a few of the entire process once this is finished. So I'm going to define 3 uniform variables here, one for each of the matrices we're using. The model matrix, of course, corresponds to the pose of the object that you want to render, the view being the position and orientation of the camera, and the projection matrix representing the lens of your camera. Next, we're going to define 3 attributes in order to allow our VBOs to stream into this shader so that we can receive our model data. First one's going to be a vector 3. That's going to be invert. But the next one here, make sure is a vector 2. I'm going to call it in UV. Pretty self-explanatory. That's going to be the UV coordinates. And lastly, we have a vec 3. I'm going to call that my in normal. So, in order to do some work on these, we'll need to open up our main function. Our task as a vertex shader is to write something to GL position before the function ends. So whatever is written into there is going to be interpreted as the vector that should be in clip space, and that will be taken through the rest of not only the OpenGL pipeline, but also that mathematical pipeline once again. So the first thing we do is we start with our vertex. However, we're going to need to start multiplying it by some 4x4 matrices. So we're going to need to expand this to a 4-component vector so that it can correctly multiply by those matrices. So we're going to add a 1 on the end in order to allow the positions represented in these homogeneous matrices to affect the vector. If that was a 0, if we did this, then what would happen is the last column of the matrix, if you remember the Rood matrix representation, where we have right up direction and our position in our last column. If 0 is at the end of the vector in the W, then that entire column essentially gets multiplied by 0, and so it has no effect. So if you ever want to rotate a vector and ensure that it is not translated in any way whatsoever, then you can always just set its W component to 0 before you multiply it by a particular 4x4 matrix. However, of course, we're not dealing with a case in which we don't want to translate, so we're going to leave that as 1. The first thing we're going to do is we're going to multiply by our model matrix, and that'll take us from object space, in which the vertex is defined, into world space. Next, what we're going to do is we're going to bring that world space representation into view space, or relative to the camera. And then once it's relative to the camera, we can project into clip space and give the result to OpenGL. So notice here that all the operations happen from right to left, and that's not just true in GLSL, but that's true in any form of matrices. It's just the way that matrices work. So make sure that you read it from right to left. We're not transforming by the projection, then the view, then the model, but instead in this direction. It's going from object to world to view to clip. So there's one more thing we need to do in this shader. And remember in the class we just had that attribute slots are all given locations. These are all going to have some ID assigned to them by default. But we don't want to rely on that. It's not safe to rely on OpenGL picking these values for us, especially if we release this code and try to run it on another system, which is running a very different version of OpenGL that might decide to do things a little bit differently for whatever reason. So what we're going to do, just like we talked about in class, we're not going to conform to what GLSL wants to do. We're going to conform this shader to what our engine wants to do. So at the start here, we're going to add some additional code, and we're going to say that we're going to call this fancy little layout thing. And inside, we're going to say that we want our location equal to 0. So that'll force that slot to be set to 0. And here, in our next one, we can use 1. And in our last one, location is equal to 2. and we're good to go. And at this point, we don't require any extra code to make sure that our VBOs, in the way that we set them up, is going to correlate exactly to what the shader expects. And let's take a look at that again really quick. We can see here we made the assumption that vertices are going to be in slot 0, UVs are going to be in slot 1, and normals are going to be in slot 2. And that, again, that information you can find in the GL vertex attribute pointer function calls. Those are the function calls that link the VBOs to the shaders. So now that that's done, we can move forward to our fragment shader, which is going to be a little bit simpler. We're not going to have anything too fancy so far. We're going to define an out vec4 called outColor, and that's essentially going to be the result of calling this fragment shader. So our job inside of the fragment shader is to write something to outColor before we're done. So let's just have some simple color. Doesn't really matter what it is. I'm just going to have something like this. And I'm going to make sure the last component's 1, just so that we have a full alpha and have a fully opaque object. There's one thing I want to mention while we're here, which is a question that you might be having, which is why doesn't it look like this, right? Why isn't this what we need to write to, where in the vertex shader we had a GL underscore position? Why do we have to define our own outColor and write to that? And there's a couple reasons. The first reason is that depending on what you're rendering to, the type of outColor might actually change. You might be rendering to a target that actually only has 1 channel, so you might actually just have a single float. You might be rendering to a channel that has 2 or 3, but additionally, you might be rendering to multiple places at the same time. Something we're not going to get into just yet, but is totally possible. And so the easiest way to do that is to use a syntax that looks like this and to be able to index into the output that you want. So because of those reasons, it wasn't as trivial for GL color to be the output in the fragment shader. But for now, this will suffice for us. So now that these two are done, we know that they're going to be loaded in. We can go back into game.cpp. Before we scroll down, I do want to finish this deconstructor first. What we're going to need is to just remove the objects that we've loaded. Previously there were no objects that were loaded as part of the game class, but now we have the pass-through shader. We're going to want to unload that, and we have the monkey shader. Sorry, the monkey object. Going to want to unload that as well. And the reason we want to do that is because those objects aren't only on RAM, but they also exist on the GPU. And the cleanest way for us to remove the memory from the GPU is, of course, to formally tell OpenGL to release those objects. And it's better to do that than to just let the program die. So if we go down to our draw function, we can actually push this mesh through really quickly because of the power of our framework. So the first thing we want to do is we want to ensure that our shader program is active. This is the shader program that we want everything to be rendering with right now. So we're going to be sending it a couple uniforms once it's bound to make sure that it's set for the current frame. So we're going to have our first mat4, and we're going to target uModel. Our model matrix being, of course, monkey transform, and I'm going to pull the data out of that, which is my float array. Lastly, we have the bool indicating whether or not we want the matrix to be transposed before we send it to OpenGL. And if you remember from my rant last year, minimath was accidentally written in row major rather than column major. So indeed we have to transpose everything we do before we put it into the eyes of OpenGL, since OpenGL is expecting column major. Next, what we have is our view matrix, and about the transpose. Of course, if you're using your own library or you're using GLM, you might not have to do that. So make sure you're aware of what data format your particular library is using. So our camera transform is going to be sent to U view, but something a little bit different is going to be done for the camera transform. We're actually going to get the inverse of it before we get the data. Now, why do we want the inverse of the camera? Well, remember that the camera, if we think about it as an object in space, in order to render everything relative to it, we can only move everything around it, because everything that gets rendered to an eye that is assumed to be at the origin. So the only way to make the camera the origin of the world is to transform absolutely everything in that world by the inverse of the camera. And so everything moves around in such a way that if you were standing at the origin and just looking straight down the negative z-axis, you would actually see from the position of where you want your camera to be. And then that gets transformed into clip space. So the reason we do this, and the reason we bother to, even though an inverse is technically slow and should be avoided, is because it's much easier to think about the camera in terms of the coordinates that it's actually at. If we didn't do this, then every single time we wanted to transform the camera, we'd always have to think in opposites. So if we wanted the player's head to turn 20 degrees to the right, we'd have to say, wait a second, okay, that means we actually have to turn everything else instead, and then you have to turn the head to the left, and then wait, but we also want to translate backwards, which is actually forwards, and it gets really confusing and hard to read. So it's much, much easier to just have the camera in space as if it was any other object, and then to simply inverse it at the end when we need to send it to OpenGL. It's totally worth the overhead of one inverse matrix call. So next we're going to be sending the projection matrix, of course. So we're going to have camera projection dot, whoops, forgot the comma there. So camera projection dot data, we just send that straight up. We do have to transpose it for the same reasons as the other ones, but that's done. And now we get to rendering the actual mesh itself, and this is where you'll see the power of VAOs. It's going to be the easiest possible way to render any object. It's so simple. All we do is we bind the vertex attribute array that we want, which is going to be the VAO inside of our monkey. We send that ID through. Then we're ready to draw, so we call GL draw arrays. The mode is going to be triangles. We're going to start at the first triangle, and then we're going to go through and draw how many? Well, let's see how many vertices we have. So we ask for the number of vertices. Then, last thing we do, GL bind vertex array 0 to remove it, and we're done. That will actually completely render the object through. So, last thing to do is to unbind our pass-through shader in order to make sure that we don't leave it bound for longer than it needs to be. If that is the case, then of course we run into a situation where somebody might be trying to do something else with shaders somewhere else in the program, and they can accidentally overwrite some of our data. It's just not safe to leave these objects bound for longer than they really need to be. So with the vertex attribute array as well, you can see that I bind it, I draw immediately, and then immediately following, I remove it since it's not going to be needed anymore. Still though, even with the unbinding calls included, the code required for sending an object through is actually incredibly concise. And this is only possible due to the fact that we're using VAOs and that we have this really nice shader program class to manage things for us. So if you're using immediate mode, it wouldn't even be as nice as this, right? So as this is done, we can actually run it through and we can see it pop up for the first time. So here we go. So we have the monkey here, although since it's static, it's a little bit difficult to get a sense of the perspective, and of course it's flat shaded, so it's difficult to get a sense for where all the polygons are. Let's give it a little bit of a spin. If we go into our update loop, at the end we can take our monkey transform and we can call rotate y, which of course rotates around the y-axis. I'm going to use delta time in order to make sure this doesn't go crazy fast. And I'm going to multiply it by 45 in order to rotate by 45 per second, 45 degrees per second. If I run it now, then I get a monkey head that's spinning. Some of you will probably recognize this object. It's a common graphics testing object. And it does the trick. So this is where I expect your code to be for this week, and you don't need to code what I'm going to do next, but I would like to take a little bit of time just to play around with a couple things to show you some other features of the framework. So one thing I would like to do is I'd like to open up a shader and I'd like to deliberately break it. So let's go into, let's say we don't convert that vertex into a 4-component vector. So this 4x4 matrix is now trying to multiply by a 3-component vector, which is not valid. If I run this now, nothing's come up here, but I can see some text has come up inside of my console output. And so something like this is invaluable for really speeding up the debugging process of shaders. So I can see here, error on line 13, error C1101. Okay, if I wanted to, I could Google that to find out some more information. Ambiguous overloaded function reference, mul mat4 vec3. It looks like it's trying to multiply a 4x4 matrix by a vector 3. Of course, that's not valid. What's going on? Let's close that. We take a look at the shader. Line 13, sure enough, we know where to look for the problem. And we can solve it much quicker than we were able to before. Say maybe one of our semicolons here is missing. If I were to run it again, line 7, expected reserved word layout, it's a little bit confused why it sees, unexpected reserved word layout, it's confused as to why it sees the layout word, because it was expecting a comma or a semicolon. So sure enough, if we look on this line, line 5, following it, we see that it has layout and it doesn't really know what's going on, semicolon, right? So just like debugging any C++ code, now you can not pull out your hair while working with shaders. And the last thing I want to do and play around with is sending data through the pipeline from the vertex shader to the fragment shader. We saw how that happens in class, so let's take a look at an example in code. So if I want to send something through, so my vertex is going to need to specify an out variable. I'm going to send a normal. I'm going to send it through. So I'm going to take my normal variable I just made and I'm going to set it equal to in normal. So that's one half of the job done. It's going to be ready to be passed through, except that the fragment shader needs to formally accept it. So we're going to specify the exact same definition except with the in qualifier instead of the out qualifier. And now this normal will have the data that was passed through, but also interpolated through the rasterizer. That's the very important key thing that we looked at in class. This isn't going to be the normal that's equal to either of the source normals on either of the vertices of the particular face. It's going to be something in between, because this fragment is probably going to be somewhere around the middle of this triangle where we never specified an explicit normal in Maya or in Blender or 3ds Max or anything. So let's use it to see that it works. Instead of these three RGB components, I'm actually just going to use the normal itself. OpenGL doesn't care about the data going through the pipeline, right? We can do anything we want. So there's nothing stopping us from using normals to output to color to the screen. Of course, it'll look a little bit funny, but it will give us something that provides a much better sense of the depth and where all the polygons are on this model. And we can see that we have a better idea now that it is rendering correctly. Notice a couple things about it. If you look at the top of the head, it's predominantly green, and that's because if we take a look at the RGB format, G is in the middle. If we overlay that with XYZ, that's the Y component of the normal fell into the green component of the color. So it makes sense that the green would be so intense on the top of the head, because the normals at that point are starting to point towards the sky, towards the y-axis. On the front of the face, you can see that the vectors are blue because the z component, or the blue component, is so strong. And from left to right of the face, you can see that it's predominantly red on one side because of the x-axis, or the red component, being strong. So we can mess around with this a little bit more and do something else. So consider that the color is rotating with the model, which means that the normals themselves are still defined relative to the model. They're still in object space, which makes sense because we didn't transform the normals in any way. We use them directly from the OBJ file or directly from the VBO. So in order to receive a different effect, we can play around with moving the normals themselves into a different space, which we're absolutely allowed to do. We have matrices that can move us from object space into world space. So let's try that first. So if I take my model matrix and I multiply it by this, of course I have to turn this into a 4-component vector so it's valid. Then this normal, by the time it gets to the fragment shader, won't actually be in object space anymore, but it'll be relative to the world, and so it shouldn't be constrained to the rotation of the object. It should be relative to the world space, and you'll see what I mean. But before, I want to mention one thing. This W component. This is one of those cases where we don't want this to be 1. Consider that a normal is a unit length vector. If we were to translate one of those, then that would break its representation of what it's trying to be. It wouldn't be unit length at all anymore. If our object was translated 20 units to the left, then all of a sudden the normal is going to receive that translation too, and it's going to completely explode the lighting calculations with all these huge normals. So what we want to do is we want to isolate this transformation to just the rotation, and we have a way in which we can do that. We can specify 0 for the W component of this vector, and then it'll only be rotated. So let's run this and see what it looks like now. Oh, what's going on? Doesn't seem to be too happy. Let me try that again. Oh, there we go. There's some problem. Oh, my mistake. And see, that's why it's so nice to have that debugger, because I forgot something and instantly I can find what the issue is. So, of course, we do turn this into a 4 by also a 4x1, 4-component vector temporarily. But then, in order to write to the normal variable here, we have to convert back to a vector 3. So I can actually put brackets around all of this and then take advantage of swizzling to extract the XYZ of the result. And if I run this now, you can see the same example again, but all the normals are no longer constrained to the surface of the object. They're kind of swimming around. Of course, the top of the head is still green, but the blue area, the part that is the positive Z, which is pointing towards the camera, is following the camera. So we're always seeing the blue side. And we can see a little bit of the red side trying to catch up. And of course, that would be to the right because that's the direction of positive X. So this gives you an idea of how data flows through the pipeline and how we can transform normals around as well. Of course, I'm going to remove this. I don't expect it to be in your projects. It's just an interesting case to look at. So I'm going to take that code out and return this back to, let's just say, solid white. Run that again, make sure we're good. Yep, there we go. So next week, we'll take a look at adding some proper lighting calculations to this to really give it some nice shading. So we're going to be building a structure to hold lights and to move them around, and we're going to be moving those into the shaders and doing all our lighting calculations by hand. But that's it for this week. So let's go through every file in case you missed anything. Go through the shaders first, vertex, and then fragment, and then I'll show the rest. And we're done for the week. Make sure again that these up here are before your GL calls. And there have been no changes to the rest of the file, but I'll go through.